Well, hello. Today we're going to be looking at combinations. Now, this is kind of an extension of what we did last time, which was permutations. These two items are often associated together, combinations and permutations. A combination is just a way of arranging things whenever the order doesn't matter. So we're going to look at a lot of examples today of when that might be the case. And if you want to see more ways of when things do matter, you can check out the previous video, which was 12.8. All right, so let's kind of get an idea of what we're doing here. Let's say a 10-member club was going to elect a president and a vice president and a secretary. And how many ways could those positions be filled? So you could almost think of it like if they're casting their ballot, right? And maybe they would write one name there, one name here, and one name here, for president, vice president, and then secretary. Okay? So in a case like this, you have 10 different people that you could feasibly choose for president, and then you would have 9 different names that you could write for vice president, and then 8 different names that you would write for secretary. And that's because you can't pick the same person for all 3 positions. That doesn't work, right? It would be impossible to have the same person be president, vice president, and secretary, and that's why these numbers went down. This was what we explored last time in the previous lesson, and you could think of this as like 10p3. 10 people that are going to be in this club, and we have 3 positions to be filled, 10p3, or 10 times 9 times 8, which of course is 720. So 720 possible ways that this could happen. This was a last time thing. Now, let's look at this next problem. 2 members of this club are going to attend a conference. And how many different ways can 2 people attend the conference? Okay, well, you might initially think like, oh, well, if we have 2 people to choose to go to the conference, it's just 10 times 9. And you might be tempted to say 90. And that's a really good guess because you're like, well, it's going to go down, of course, because if you pick, Shelley to go, for the first one, you couldn't also pick Shelley to go for the second one, right? You couldn't do it that way. So therefore, it's going to be 10 times 9. So you pick Shelley for the first, and you pick Sally for the second one. They're different. But here's the difference. Does it matter if it's Shelley then Sally, or if it's Sally then Shelley? No, that's the same group of people. It doesn't matter who was picked first in this case, because now we're talking about a group of people that are going to go. In this case, it's a pair of people. And so it's easy enough when we're only working with 2 people to say, oh, so we're just going to cut it in half. There's actually 45 different groups of people that might go on this trip. And again, that's because the order doesn't matter, right? Because if you pick John and then Matt, that's the same thing as Matt then John. They're the same group. And so what that means is we're actually, if they're the same, if it's the same group of people, we have to get rid of those repeated ones. And that's where this idea of a combination comes in. Okay, it's a distinct group of objects without regard to their arrangement. No arrangement. We're not lining up, not like last time. This, we're talking about a group of people. Typical problems that involve combinations are anytime you see a group, a team, a committee. If you see, I don't know if I spelled that right. Whatever. Anytime you see those types of words, groups, teams, committees, those are all going to be combination type problems. Whenever you see line up or arrange or running a race, when you see those kind of things, those are going to be permutations. See, combinations, when you're talking about a group, the order doesn't matter. And in actuality, this formula, it should look pretty familiar, because if I were to just get rid of this little part here, then this would look a lot like the permutation formula that we did last time, right? And then this other part over here, dividing by the repeated values, that's what we did when we were talking about unique arrangements with the letters. Specifically we looked at words Tallahassee, and we looked at bookkeeper, right? And maybe you looked at Mississippi. I don't know. But that's just dividing out the repeated ones. So this formula for combination is actually kind of a combination of those two ideas. It's taking that permutation formula, the number of ways that you could arrange something or line something up, and then it's dividing out the repeated ones. Okay, so that's where this formula comes from. Now, let's take a minute and look at one by hand. 8C3. And then we'll also look at how you can do this on the calculator. So according to our formula, it's going to be, which is n factorial, n minus r factorial, r factorial. So that's 8 factorial over 8 minus 3 is 5 factorial, and then 3 factorial. Okay? Well, that's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Actually, I think combinations are actually a lot of fun. I do them by hand quite a bit. Okay. Then we get to talk about doing some canceling. And I notice here that I have 5, 4, 3, 2, 1 and 5, 4, 3, 2, 1. I can get rid of all of those just like that. Bam. And then I can say 3 times 2 times 1, that's 6. That will cancel with the 6. And then 8 times 7 is 56. You see, a lot of these combinations we can do by hand when they're smaller. I mean, if this was like 54C12, now I'm not going to do that by hand if I can help it. But on your calculator, right where we were at before with permutations, which on the Casio is under options, and then we got an arrow over, so we'll hit F6, and we'll go to probability, that's our F3, and then right here we have our NCR. So 8C3, remember, is talking about picking 3 items when order doesn't matter. Okay? 8P3 would be how many ways you can arrange those items. Like if there were 8 people running a race and you were going to have 3 of them get ribbons, then you would use 8P3. But that's not this problem. C is talking about a team or a committee when order doesn't matter. Okay? So that's what this comes down to. All right, let's go ahead and explore the TI calculator real quick. In order to do this, I'm going to first turn it on, and we're going to hit 8, and then I'm going to go up here to math. We arrow over to probability, and then scroll down to NCR. Then we'll do 3. 8 NCR 3, and right now we've got our 56. Okay, so same way. Let's go ahead and see what some of these problems are going to look like. Okay. So the first one we have here is Jan is a florist, and she has 10 different cut flowers from which she's going to choose 6 of them to put in a floral bouquet. How many different ways could she do that? Now, we're going to talk about like a bouquet of flowers. It doesn't necessarily, it doesn't matter like which one you put in first, which one you put in second, which one you put in third. Now, I know there's maybe some people out there that do floral arrangements and they're like, oh, he's so silly. Of course it matters. For our sake, it doesn't. Okay, it's a whole bouquet. It doesn't matter which one went in. The fact is they all look like that now. Okay, so this is a way when we're talking about picking 6 flowers and we're going to put them in a vase. So it doesn't matter which way we put them in. This is a combination, so we are going to use 10C6. 10 flowers to choose from, and we're going to pick 6 of them to put in our bouquet. So that's going to be 10 factorial over 10 minus 6 factorial, and then 6 factorial. Notice these two, they're going to just add up to be 10. Just like in the last one, the 3 plus 5, those added up to be 8. 10, 9, 8, 7, 6, 5. Oh, I'm so bored with writing this all the way down. 5, 4, 3, 2. I knew that that's what it was going to be. right? And then I have down here, I have 4 times 3 times 2 times 1, and now I've got 6, 5, 4. If only there was a way of writing 6 times 5 times 4 times 3 times 2 times. Oh, that's what that is. 6 factorial means to do that. 6 times 5 times 4 times 3 times 2 times 1. In fact, up here, I could have just done 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's what that means. So this is kind of a little shortcut way of writing it. You can write it all out if you want to. Nothing wrong with that. It's just way easier to just write out what you need to. All right. 4 times 2 is 8. So I'll cancel that with the 8. And now I have 3 goes into 9 3 times. So up top, the only thing that I have left now is a 7, a 3, and a 10. Of course, you can put them in any order because of the commutative property of multiplication. 3 times 7 is 21, times 10 is 210. Notice there is no denominator. So there's 210 possible ways that you could make these bouquets if you have 10 different flowers to choose from and you're going to pick 6 of them. Okay. Of course, on our calculators, we'll just go ahead and double check that. We'll do 10 C 6. Okay. All right. Let's see here. Just showing you something here. 10. What if we were only picking 4 of the flowers to make an arrangement? I wonder how many arrangements we would have then if we were only picking 4. What? Think about that there for a minute. We picked less flowers, and yet we still had the same number of arrangements? Just think about that for a little bit. All right, you want to purchase 5 of the 7 CDs that you like. So you got 7 CDs in your hand. You're like, I can only afford 5 of them. Nobody buys CDs anymore, but it's whatever. Maybe you're in a vintage shop. So you've got 7 of these albums, and you want to purchase 5 of them. How many ways could you select the 5 items for purchase? Well, again, it doesn't matter the order. The fact is that you're going to buy them. And then you're going to buy them, and you're going to throw them in your bag, and you're going to walk out of the store. It doesn't matter which one you scanned first and which one you scanned third. And if the order doesn't matter, then we're talking about a combination. 7C5. So this will be 7 factorial over 7 minus 5, which is 2 factorial, 5 factorial. 7 times 6 times, look at this, I'm just going to do that. Because that means keep on going. The reason I'm going to do that is because that's the bigger of these two. And you don't have to do it this way. It's just a shorter way. It's a nice, clean way of doing things that just allows you to do some canceling without being too sloppy about it. Those are gone. 2 goes into 6 3 times. And now we've got 7 times 3 is 21. Let's go ahead and confirm that on our calculator. We'll do 7 NCR 5. And we got 21. Right? By the way, just throwing this out there. What about 7C2? What if instead of buying 5, what if we could only afford 2 of those albums instead of 5 of them? I mean, we probably wouldn't have that many ways of doing things, right? We probably wouldn't be able to do that very minute. It's 21. It's the same. 7C5 and 7C2 are the same. Well, let's go ahead and think about that for a minute. 7C2 would be 7 factorial over 7 minus 2, which is 5 factorial, 2 factorial. And then, of course, because of the commutative property of multiplication, we could read those are the same. Now, while that may seem kind of strange, let's understand the reasoning behind this. There are 21 ways in which you could select 5 of those albums to purchase, right? Now, let's think about it in kind of a different way. What if you were holding those 7 albums in your hand and you said, man, I can't afford to buy two of them. I got to put two back. So how many ways could you pick two albums to put back on the shelf? Well, it turns out that there's 21 ways that you could put two albums back on the shelf. And if there's 21 ways for you to put two albums back on the shelf, then that means you can walk out of the store with 21 different ways of selecting five. You see, 7C5 comes out to be the same amount as 7C2 because when you choose five albums to keep, you're, in a way, choosing two to put back. Or the other way around, like when you're choosing two items to put back, you're also thinking about ways that you could keep five albums. And so those are directly connected. It's not coincidence that those come out to be the same. You're going to have a dinner party. There's 10 different bottles of soda and 8 different bottles of juice. You want to have 4 bottles of soda and 2 bottles of juice sitting out on the table, right? Like you can't fit all of them out on the table for your party guests all at once, so you just put a couple out at a time, right? And you know that people prefer soda over juice. So how many ways could you choose your beverage? Well, if you have 10 bottles of soda, when you're putting them out on a table, once again, the order doesn't matter. We're talking about combinations. 10 bottles of soda, and we are going to choose 4 of them to sit out on our table. Now, you also have some juice. We have 8 bottles of juice, and we are going to pick 2 of them to put out on the table. So maybe this is our first table, and over here we have a whole nother table, and we have 8 different juices to choose from, and we're going to put 2 juices out. Ultimately, because of the counting principle, we multiply these. So it's 10C4 times 8C2. Now 10C4, that's actually one that we've already done. We did this one earlier in this very lesson because we did 10C6 and we got 210. And then we discovered that that with the flowers. And that's the same as 10C4. It's 10C6 and 10C4 are both 210. 8C2, you can do that one on the calculator. You can do it by hand. It's not too bad. 8C2, and that gets us 28. Now, if we multiply these two numbers and we take 210 times 28, that will get us 5,880 possible ways of setting out our juice and soda. Now, you could also actually just do this all in one go if you wanted to. You can say, 10C4 times 8C2. And your calculator knows what to do. Like it's gonna do this in the right order if you're doing this right. Okay, so there's that. Now the last problem for us to look at is sometimes when you go to a restaurant, you can order things like family style. If you're there in a large group and you want to order some family style things, they might say like choose this many from column A and this many from column B, and of course you always got to think of Aladdin. I can't help but think of Aladdin for that, but I can't sing it here because I don't want to get copyright infringement. Also, I don't want anyone to cry from my singing, so I won't. But there's a large group of people, and they get to pick 3 items from column A. I'm sorry. There are 3 items from column A. There are 4 items in column B, and 3 items in column C. Okay? Oh, that's how many they get to pick. And each one of those has 5, 7, and 6 respectively. So column A has 5 and they get to pick 3. That sounds like a 5C3 kind of thing. Then for column B, they get to pick 4 and it has 7 choices, 7C4. And then for column C, maybe that's the dessert column, they have 6 desserts to choose from and they get to pick 3 of them. So that'll be 6C3. And then ultimately you can put this all in your calculator. These aren't that hard to do by hand, especially these. These are all relatively small, right? Because this is 5 factorial over 2 factorial, 3 factorial. This one will be 7 factorial over 3 factorial, 4 factorial. And then 6 factorial over that. Okay? Um, let's see, 5 times 4. We'll go ahead and might as well do all this. We've already come this far. Let's finish it together. 7 factorial, of course, is 7 times 6 times 5 times 4 factorial. And I'll just put the 4 factorial down there, and we'll do 3, 2, and 1. And then over this one, 6, 5, 4, 3 factorial over 3 factorial, and that's also 3 times 2 times 1. Then we can do some canceling. Right, clearly that goes, that goes. That makes 5 times 2 is 10. For this one, 4 factorials are gone, and I can take 3 times 2 is 6, and there's a 6 factorial right there that cancels. Notice that with combinations, your bottoms will always cancel all the way out. This is a 1, right? It doesn't matter. 7 times 5 is 35. And then over here, those are gone. And once again, 3 times 2 times 1 is 6. And then we have 5 times 4 is 20. The next thing I would do is to take 2 times 35 and make that 70. And I'd add 2 more zeros on. So that makes 7,000. There's 7,000 possible ways that a family of 8 could sit down at this Chinese restaurant and get their food. Right? Now we can always double check that here, and so it's never a bad idea. Let me tell you, if you're ever making some YouTube videos for people, it's always a good idea to double check. That way you don't get too much hate mail about how wrong you are. So we'll go ahead and double check this. We'll do times 6c3. Now, in truth, I've worked this out many times before, knew the answer, but I just wanted to show you that you can put all that in your calculator too and get away with it all in one go. All right? Well, I hope that this has been valuable to you in some way for your learning of combinations. Remember, combinations are a group, a team, a committee. The order doesn't matter. Order doesn't matter with a combination, right? It's like just taking a handful of something. The order doesn't matter. When you're talking about arrangements, that's permutation. That's the other lesson, okay? When you're lining up, when you're running a race, right? When you're arranging, those are all permutations. That's not this lesson. That was the other one. All right, well, good luck with distinguishing between these, and make sure you can do some of these by hand because it's good practice doing some canceling. All right.